All right, back for part 3. So I'm going to walk you through a problem in your problem set on page 114, number 55. Again, I may have assigned this. If I didn't assign this one, I assigned one just like it. So we're going to use combustion data to find empirical and molecular formula. So the problem states this: menthol, which is a substance in mentholated cough drops, has carbon, those are commas, hydrogen, and oxygen. And the problem states if 0.1005 gram sample is burned in oxygen, it will produce that amount of carbon dioxide and that amount of water. And the question is, what is the empirical formula? And then also, what is the molecular formula if the molar mass of 156 grams per mole is given? Remember, I said you're going to need the molar mass if you're going to be asked to find the molecular formula. Okay, so here's what it looks like. I have carbon, these are commas again, hydrogen, and oxygen in my hydrocarbon. And I know the mass of it. I know it reacts with oxygen. We're going to talk about combustion reactions in a few minutes. I know it reacts with oxygen, and a combustion reaction always produces carbon dioxide and water. And so I know the amounts of each of my products. So what I do is I take the 0.2829 grams of carbon dioxide and I look at what is the gram ratio between carbon and carbon dioxide. What is the percentage that of this molecule that's carbon versus the carbon dioxide? So I find out by doing this calculation the grams of carbon. Once I get the grams of carbon, I then convert to moles. Remember, grams are not going to help you with anything in these formulas. It's all about the mole ratio. So I'll calculate my value for the moles of carbon. Now I'll do the same procedure with the water. I can say, all right, what percentage of this water is hydrogen? Because whatever hydrogen is here has to be the same amount of hydrogen in grams that's here based on law of conservation. So if I have it as a reactant and as a product, they have to be equal. So I use 2.02 for the hydrogen because there's two of them. The atomic mass of hydrogen is 1.01, but since I have two in my water molecule, I use 2.02. Out of the 18.02, I find out what is the mass of hydrogen in that water molecule, and then I convert that water molecule to moles. But this time I use just the value for one because I now have an absolute value for the grams of hydrogen. Now I'm just going to convert that grams of hydrogen to moles of hydrogen, not H2. So I get a mole value. Then I do that same process where I pick the smallest value, and the smallest value, oh, sorry, I missed a step. So then I have to find the oxygen. So what I know is that if the whole molecule, the C, H, and the O are the 0.1005, the original amount of the sample, if I know how much is carbon, which I calculated here, and I know how much is hydrogen, which I calculated here, and I subtract each of those away from the carbon, hydrogen, and oxygen, then what I have left is the grams of oxygen. Then I take those grams of oxygen, just like I did for the carbon, hydrogen. Now I'm going to convert that to moles. So of these three mole values that I've calculated, this one, and this one, I pick the smallest, which is the 0.0006438. I divide each by that smallest, and I get my whole numbered mole ratio. Everything is close enough to a whole number so that it becomes 10, 20, and 1. So my simplest formula then is here C10H20O. And if I were to stop the problem there, that would be my answer. But the following question is, what is the molecular formula? So I plug into that formula where I take the empirical formula, multiply by X, set it equal to the molar mass, 156, which was given in the problem, and I then solve for X and distribute. But what I find in this one is that X is equal to 1. And in this scenario, the empirical formula is the molecular formula. So I'm stopping there.